So how do we characterize conduction process and heat transfer rate in two-dimensional systems? So as a rule of thumb, natural systems, the tough part is going from 1D to 2D. Going from 2 dimensions to 3 dimensions is just a matter of routine repetitive procedure. For instance, what you will see is that you will start seeing multiple eigenvalue problems when you actually go from 2 to 3D. So we will not discuss 3D systems in this class. I would like to bring to your notice that 3D system is just an extension of what you would see in a 2D. So let's take a simple slab, a 2D slab, x direction, and this is y direction. Okay, so you need two coordinate systems, and let's say the length in the x direction is L, and the width, let's say, is W. Okay. And in principle, if it is 3D, there will be a third dimension which is outside the board. Okay. And let's say that we maintain 3 sides at a constant temperature T1, and let's say the fourth side is maintained at a temperature T2. So I assume that T1 is not equal to T2. Okay. And if I assume that Q dot equal to 0, that is the net rate of heat generation per unit volume is 0. Okay. I mean, in principle you could include that also, but let's say to start with, the net rate of heat generation inside the slab is 0, and if I assume that it's a steady state condition, right? So what are the processes which are involved here? What are the processes? Only conduction, right? So in a general system you have conduction and heat generation. So here you have only conduction which is involved. So the model is very simple. So K del square T equal to 0, right? We said it's steady state, so accumulation is 0. And so if I open up the Laplacian, it will be d square T by dx square plus d square T by dy square. That's this. That's the model. What are the boundary conditions? Very easy. I've specified the temperatures. So there are 4 temperatures in 4 boundaries, and that's going to be the boundary condition. So T, so I'm going to use 2 coordinates as x and y, and so x comma y equal to 0. The temperature is T1, okay, and that's also equal to T of x comma 0 comma y. It's also equal to T of x comma L, which means that at x equal to L, any y, the temperature is T1, and similarly in these 2 surfaces. And the fourth boundary condition is x equal, at any x and y equal to W, the temperature is T2. Okay. So how do we solve this? What about x direction? Okay, well, not quite so. So it's slightly different. So you use what is called separation of variables. So if you knock off one by one, then you will see that the eigenvalue problem that you will get will actually not be a closed form eigenvalue problem. So it is better to assume upfront that the separation of variable means that the x and y dependence of these two, x and y dependence of this equation are independent of each other. Is that a correct assumption? Why is it that separation of variables works for this? Does anyone know? So whenever you have a linear problem, okay, so linear problems, they have this property that you will be able to decompose the linear problem into its multiple linear components. So it's linear in both x and linear in both x and y direction. Therefore, the solution has to be a product of 2 functions where each of these functions are dependent only on that coordinate system. So the way to do that is you make a substitution, okay, not like the way we did before. So we said theta is t minus t1 divided by t2 minus t1. So now we use a dimensionless quantity. So note that theta is a dimensionless quantity. You have a ratio of temperature difference with another temperature difference. Okay. So this is the first time you start seeing a dimensionless temperature in this course. Okay. I mean, you could still use the original change of variables that we did, but this is just makes your life a little easy in terms of the solution, and the solution comes out in a much more elegant fashion. Okay. So now we assume that theta equal to some capital X, which is a function of only X position, and another function Y, which is a function of Y position. Okay. So now I substitute this equation into the original model. So it will be d square theta by dx square plus d square theta by dy square equal to 0. So now if I substitute the separation of variables, so representing the solution as a product of two different independent functions is what is called as separation of variables. So I can write this as y into d square x by dx square plus x into d square y by dy square equal to 0. Okay. So all I have done is I have substituted theta and then just evaluated the derivatives. Now I can rewrite this as minus 1 by x d square x by dx square equal to 1 by y d square y by dy square. So I can rewrite the expression like this. Okay. So the left hand side, if you look at the expression here, the left hand side is only a function of x direction, and the right hand side is only a function of y direction. So what should be each of these quantities? If you have two functions, each of these are function of different coordinates, and if they are equal, then they should be a constant. So if we assume that this is a constant, so if I put lambda square as the constant, because these are completely independent functions, and only way by which two independent functions can be equal to each other is when these two functions are a constant. And so if that constant is lambda square, so I can now break this down into two independent eigenvalue problems. So minus 1 by x d square x by dx square equal to lambda square 1 by y d square y by dy square equal to lambda square. I can break this down into two eigenvalue problems. What is the general solution of the first problem? What's the general solution? Yeah, cos and sine. So note that the eigenvalues are now imaginary. So x will be c1 cos lambda x plus c2 sin lambda x. And what about the general solution for y? It's exponential. So it will be c3 exponential of lambda y plus c4 exponential of minus lambda y. Okay. So theta is now equal to c1 cos lambda x plus c2 sin lambda x multiplied by c3 exponential lambda y plus c4 exponential minus lambda y. Okay. So that's the solution. So this is an excellent example of where some of the concepts that you've learned in your math courses are directly applied to engineering systems. So the boundary conditions are theta at x comma y equal to 0. So x comma y equal to 0 is, what's the boundary condition? So note that theta is defined as t minus t1 by t2 minus t1. So this is 0, right? And that's also equal to theta at x equal to 0 comma y, and that's also equal to theta of x equal to L comma y. And theta at x equal to x comma y equal to w, that will be equal to 1. So in fact it is for this reason why we chose that type of a scaling. So your boundary condition essentially becomes 0 and 1, and it helps in solving the problem. So if I impose the first boundary condition, that will be 0 equal to, so any x and y equal to 0. So if I set y equal to 0, so then it will be C1 cos lambda x plus C2 sin lambda x multiplied by C3 plus C4. And if I put the second boundary condition, that x equal to 0, we will have 0 equal to C1 cos lambda x multiplied by C3 plus C4. So from these two you can easily read out. So cos lambda x is the eigenfunction of the eigenvalue problem, and that cannot be trivial, which means it cannot be 0. So therefore this imposes that C1 equal to 0, and this imposes that C3 equal to minus C4. Okay. So that's what these two boundary conditions will impose. So now theta equal to C2 sin lambda x into, I can pull C4 out here, so e to the power of lambda y minus e power minus lambda y. Okay. Yeah, that's fine. So e power, yeah. Yeah. No, not necessarily. Not necessarily. So you will come to the third boundary condition. Right, so it will all from 3 solve. So it's fine, you can put the third one here. It wouldn't matter actually how you put them, it wouldn't matter, you will get the same solution. Okay. So the third boundary condition you can impose and say that C4 C2 sin lambda L into e power lambda y minus e power minus lambda y equal to 0. Okay. So what's the solution of this problem? Sin lambda L equal to lambda equal to 2n pi by L. Is that the solution? N pi by L. Okay. So the reason is, if C4 or C2, if either of them are 0, then the solution theta is always equal to 0. So you know that theta is not 0. So therefore sin lambda L is the one that has to be 0. So sin lambda L equal to 0 means lambda equal to n pi by L. What is the value of n? Integer, any integer except 0. Why? You get a trivial solution. If you plug in lambda equal to 0, if you plug in n equal to 0, then lambda is 0 and sin 0 is 0. So what you get is a trivial solution where the temperature everywhere in the slab is 0, but we know that's not the case. So therefore the permissible values for n is going from 1, 2, 3 up to infinity. So those are the permitted values of n that can be applied here. Okay. So now comes the fourth boundary condition. So theta equal to C2 C4 into sin lambda x into e power lambda y minus e power minus lambda y. So I can now replace this as sine hyperbolic. Sine hyperbolic is just e power lambda y minus e power minus lambda y divided by 2. So this is 2 times C2 C4 sine lambda x into sine hyperbolic of lambda y. Okay. And as lambda goes from anywhere between 1 to infinity, so you will get different values of constant for every value of n. So therefore theta n will be Cn sine lambda x into sine hyperbolic of lambda y. Okay, so that's the value of theta for any n, but it's a linear problem and all of these are the likely solution. Therefore theta is nothing but sum of n going from 1 to infinity Cn sine lambda x into sine hyperbolic of lambda y. How do we find Cn? By plugging in fourth boundary condition, by normalizing. Which one? No, it's actually both. So when you plug in the fourth boundary condition where you say y equal to w, so 1 equal to sum n equal to 1 to infinity Cn sine lambda x into sine hyperbolic lambda w. So you still have to find Cn. So you use the property of the eigenfunctions. So all the eigenfunctions for individual values of n are orthogonal to each other. So sine pi by L is orthogonal to sine 2 pi by L, and both these are orthogonal to sine 3 pi by L. Okay. So if you use the orthogonality condition, so normalize using orthogonality condition. Orthogonality condition. So you will find that Cn is given by 2 pi minus 1 to the power of n plus 1 divided by n. It's 1 by sine hyperbolic n pi w by L. So n going from 1 to 3. Okay. So that's the value of Cn, and these are the isotherms that you will get. These are the constant temperature lines that you will find on the slab. Okay. Final expression. So the steady state 2D So we said that Cn, which is the coefficient in front of the series summation expression, that's given by 2 by pi and minus 1 to the power of n plus 1 by n into 1 pi sine hyperbolic n pi w by L, n going from 1 to 3 etc. And the solution is 2 by pi by n sine n pi x by L sine hyperbolic n pi y by L sine hyperbolic n pi w by L. Okay. So that's the solution. So let's just quickly look at what is the temperature profile and discuss a little bit about that before we march forward into the next topic. Okay. So 0 to L is the length in the x direction and 0 to W is the width in the y direction. And according to the definition, okay, so that's the temperature specification along the boundaries, and so the profile would be that, so this is the isotherm. So in principle you could draw a three-dimensional picture, you can draw a three-dimensional surface of how the temperature is going to look, but the other way to do is what is called the contours. Okay, so this is a contour drawing. It's a contour, and contour is essentially every location you use either the isotherm line, or if you have colors you could represent the temperature with colors. Okay, so this is the constant temperature lines along this slab here, and naturally it has to be in the decreasing theta. So as theta goes down, so you can see this would be like, could be like 0.75, theta is 0.5, 0.25, etc. So these are the isotherms or constant temperature lines. Is that clear to everyone? In fact, it's not hard to plot this and see. So in fact, one should do that. So if I think you must be introduced to MATLAB by now in your numerical course. So you should take and plot this expression and convince yourself that this is the temperature profile that you will get. Okay. So there are some very simple tools in MATLAB to actually draw contours and 3D pictures. So whichever way you could actually plot them, and you should convince yourself that this is the solution. Okay. Any questions so far? Okay. So the next aspect of the course is we call lumped capacitance method. We've already come across the word lumping. So remember a couple of lectures ago, I told you that when you want to crash a certain dimension because you want to assume that the gradients are negligible in a certain dimension, then you integrate, and what you do is called lumping.